Okay, as you saw in the opening slide, we're doing two things. We have two objectives. We're going to either solve equations or find equations that have no solution or are identities, which you'll see what those mean in a minute. But this one right here is just can be solved. Okay, so this is what we're going to do. Notice the new thing that we're adding here is that we've got the variable on both sides, and that's what this says. Okay, so how do you do that? Well, how do you get started? There are variable terms on both sides, so you got to decide which variable term to add or subtract so that you've got them all on one side. Essentially what we're going to do is we're going to first get rid of the variable on one side. And in fact, what we're going to do here on this step is we're going to subtract the 2x from here and then also subtract 2x from the other side. And that will, when you do that, you see that here's the original equation unchanged. Here we're subtracting 2x from both sides, and that's going to cancel it out from right here, okay? And we're left with 14, and now there's only variables on this side. Since we got all of the variables to the left side, we're going to get all of the constant terms to the right side, which means that we're going to get rid of it off of this side by subtracting 2. And then we're just left with 3x equals 12, and it's simply a matter of dividing by the coefficient in order to undo it and get it to 1x, which is 4. Now, could we have subtracted 5x from both sides instead? We could have, and in fact, that's going to be part of your got it problem, is to say, what if instead of subtracting 2x from both sides, we subtracted 5x and moved them over here, okay? And that's the big idea. So if you want to do a proof on this, watch what you do. We write the original equation unchanged. Everywhere there's a variable, we put parentheses and the value inside. And then what we're doing is this is a numerical expression on this left side. There's nothing that we need to do in order to simplify it to a single number. We can treat it like it's an expression and not one side of an equation, right? The expression is like if you were just given 5x plus 2 and then said plug in a 4 there. We can simplify that down to 22. Over here we can do the same. You might, if you're writing it out, do the intermediate step, which would look like this, of 5 times 4 is 20, plus 2, and on this side 2 times 4 is 8, plus 14, and have that as an equivalent expression, or an equivalent equation rather, so that you're showing what you're doing in between, because you're doing 2 steps here. If you don't do that, you're doing multiplication and then addition to get right to 22. So this shows just the multiplication part, okay? But if you left that out, that's okay. Ultimately, we get down to both sides the same, and we say, check, we did that correctly. Now, you've got a got it problem, and for the got it problem, again, you're going to first solve a problem, but then this one is asking you to solve this same one from up here, but by subtracting 5x from both sides. And you should do that and see what it looks like to do that. Give it a try. All right, this problem is an application of the idea in a word problem. And the idea here is that it takes a graphic designer 1.5 hours or an hour and a half to make a page for a website. Now, if this graphic designer were to use the new software, she could complete the page, each page in 1 1/4 hours, 1.25 hours, but she would have to learn the software in order to do that, and that's going to take 8 hours. So how many web pages would the designer need to make in order to save time using the new software? So first we're going to find out how many pages would she need to make in order for it to take the same time, okay? But what do we know? Okay, it takes an hour and a half per page right now. There's the time for the new software is time when using the new software would be just an hour and a quarter, but there is time to learn the new software, which is 8 hours, okay? So what do we need? The number of pages the designer needs for her to be saving time. And we're first going to find an equation which will say at what point does she spend the same amount of time to make the same amount of web pages, either using the original software and taking an hour and a half for each one, or using the new software, hour and a quarter plus 8 hours to learn it. So what does that look like? Okay. current design time would be, watch, 1.5 hours times however many pages, because one page will take an hour and a half, two pages will take 3 hours, etc. Okay, so you multiply that hour and a half per page times the number of pages. Or you could do 1.25 hours per page times the number of pages, but have to add on that extra 8 hours and set them equal to each other to find out at what point do you have an equal amount of time for an equal amount of pages. So solving this equation is, you see the variable on both sides. We're going to move, since there's variable over here but no constant, it makes sense to take this and get it to that side, and then you just have constants on one side. I'm sorry, variables on one side, constants on the other. Okay, so subtract 1.25p from both sides. And once you get here, what you're doing is you're dividing by 0.25 or dividing by 1/4. That's the same as multiplying by 4, and that's why you go from 8 to 32. Okay, so what's the answer then? It'll take the designer the same amount of time to make 32 web pages using either software. So this designer must do at least one more page at the faster time in order for her to save time with the new software. Yep. Here's your got it problem. See how you do. All right. This problem essentially has you needing to do the distributive property to simplify each side before we get going any further. And you can see why in Unit 1 we practice the distributive property, because it now comes up in the context of a larger, more complex problem. So we need to be able to do it. And essentially that's what we've got to do. Now, how do we get started? Remove the parentheses using distributive property. Great, let's do that. And when you do that, distributing this, you get 10x minus 2 equals 3x plus 33. And now we're back to one of those variable on both sides type of problems we did earlier in the lesson. And if you subtract 3x from both sides, then what you're going to be left with is a positive coefficient on the variable. We could also subtract 10x. And if you did the got it problem on that earlier one, problem 1, you would have, and you subtracted 5x, you would have gotten a negative 3x. That's fine. All you have to do is then divide by a negative number. But for kids that are shaky at that, it might not be, that might be an area that would cause you problems. So taking away this 3x leaves you with a positive number of x's, which means you're dividing by a positive number eventually. So that's better. Now, subtract 3x from both sides, you get this. You know how to do these two-step problems. Add 2 to both sides, divide by 7. There you go. That's what you get. Yeah, and you can try this with the got it problem. By the way, you could do proofs on these, and you should know how to do proofs on these. In fact, let me just back up a second and say, if you were to do proofs on these, it would look like this. You would start with the original equation unchanged. Just write proof here. I'm not going to do the whole proof, but I want you to see what it would look like as a setup. You write the original equation unchanged. Because what you're going to do next here is substitute in for the variable a set of parentheses and the value. And when you put parentheses inside, the outside becomes brackets, and you say, what are we putting in there? We're putting in a 5. And here you would say 3. That becomes brackets because these parentheses are here for that x. And you put in a 5. And essentially then you can say, okay, now I can just follow the order of operations, and I can first simplify this. 25 minus 1 is 24. 2 times 24 would be 48. And here I would do these two. That would be 16. 3 times the 16 would be also 48. So that's how you would do the proof if you were going to substitute parentheses inside parentheses, is to make the outside parentheses brackets. We're not necessarily asking you to do proofs on every single problem, but you should know how to do proofs on every single type of problem and be prepared to do a proof on a problem if we say do a proof on this problem, because we want to see you know how to do it. So make sure you understand how to do the more complex ones as proofs as well. Anyway, here's your got it problems. Good luck. Okay, so in the previous slides, we just did different ways of solving equations, which is really just applying different things you saw, like the distributive property, to new, kind of more complex problems, but it was still just solving them. This concept is different. There's an idea here that there are certain equations where it doesn't actually matter what value you put in for the variable. There's no one number that solves it. Everything that you plug in is going to make it true. An equation that is true for every possible value of the variable is called an identity. Remember, an identity is like 1 equals 1. Something is equal to itself. Okay, well, x plus 1 is equal to x plus 1. That's the exact same amount no matter what x is. And you can see it like this. Let's say we take that equal amount x from both sides. We're left with that statement 1 equals 1. Is that true? Yep, that's true, always. Okay. That's one possibility, is that it's always true. The other possibility is that there's no value that makes the equation true. Okay, an equation has no solution if there's no value of the variable that makes the equation true. Makes sense, right? No solution. Just it's right there in the way that you say it. The equation x plus 1 equals x plus 2 has no solution. And if we did the same thing here, you could see, what if we subtracted the same value, same amount away from both sides, that x amount, whatever it is, it's the same amount from both sides, we get 1 equals 2. When is that true? That's never true. Now, visually, it looks like this. Let's say x is some number. Let's say x is the number 3. Okay? Well then, x plus 1 says start at the same place on the number line and move the same direction, the same number of places. Where are you at? You're at 4 for both. You're always going to land on the same number. What if instead of x being 3, x was negative 9? Say we started down here and we did the same thing. We took that value of x, which is the same on both, and we advanced 1. We increased it by 1. What do we get to? Same number, no matter what. No matter what value of x is and where we start on the number line, doing the same thing to the same number is always going to result in the same number. Okay, that's the idea with an identity, is no matter what value of x is, you're starting at the same place on the number line, and then you're doing the same thing to the same number. You'll always land on the same number at the end of it. Now, for a no solution situation, like x plus 1 equals x plus 2, we would say, okay, let's say x is equal to negative 4. We start at negative 4 on the same number lines. Okay, now what do we do? Well, for one of them, we advance 1 plus 1. And for the other one, we advance 2 plus 2. Do we land at the same number? Nope, we land at different numbers. And in fact, let's say x was a different number, like 6. Start here at 6. For this one, we start at the same number, but then we advance 1. And on this one, we advance 2. Do we land on the same number? No. In fact, as you can see, if you start at the same place and then you do different things, you're going to end up at different locations. And with both of these, identities and no solution, the idea is that you're starting at the same place. And what does that look like in the equation? Well, that is, starting at the same place means you have this starting value of x, and then you do the same thing. That's an identity. Here, on the right-hand side, you start at the same place, x, and then you do different things. Okay, that's the big idea, but you have to start at the same number. Now, it doesn't have to be just x. It could be like 5x. 5x on that side is the same as 5x on that side. So if you did the same thing, minus 3, you're first starting at the same number. 5 times x is going to give you some number, same each place, and then you're doing the same thing to it. Versus if you had something like negative 7x on both sides, and then you did different things to it. Plus 5 here, minus 2 here, okay? Oops, and I should be writing the x there as well. Sorry, it's negative 7x, okay? This is just going to be some number, and this is going to be the exact same number. So that means you're just starting at the same place on the number line. And then what are you doing at this part? you're doing different things from the same starting place, of course you're going to end up in a different location. That's the big idea, and we're going to apply it. All right. Notice just here, I've copied this over here. If it's the same on both sides, it's an identity. If it's different on both sides, it's no solution, assuming that we have the same amount of the variable. So what is the solution? Do we have identities or no solutions for these? Well, if we look at this, it's not apparent right at the start because we need to simplify it and see what we get. But when we do that, you see that distributing that 2 into the 5x plus 6 gives you 10x plus 12. And that is the same on both sides. It's always true. Remember, 10x is equal to 10x. So we're starting at the same place, and then we're doing the same thing to it. That's always true. So there are an infinite number of x values that would make it true. We call that an identity. Okay? Versus this next one, where we have to actually combine the like terms. It's not clear, again, what we're seeing until we combine these like terms of negative 3m and 12m. But when we do that, we get 9m minus 4 equals 9m plus 5. And they say, okay, well, let's subtract the same amount from both sides to see what we get. You could have done that here. You could have subtracted 10x from both sides and got 12 equals 12. That's clear that that's equal. Here they subtracted 9m from both sides, leaving you with just this. But you could have also just looked at this line right here and said 9m is the same as 9m. That's starting at the same place on the number line. And now we're doing different things from that same starting place. We're going to end up at different locations always, no matter what 9m was equal to. No solution. Okay, try these got it problems. Okay, I highly suggest you practice these. Kids mostly struggle with the, is it an identity, is it no solution, and what does that mean? And that's why I spent some time on this video really laying it out. Try these lesson check problems, see how you do, see if they match with the answers so that you know what you're doing. Good luck.